Hello everyone, I'm Abhinay Tuniki. I'm currently in my third semester of ADTA course. So let's start with the introduction. The present study initiated an investigation into complex realm of recurrent neural networks, with particular emphasis on their use in prediction of time series data. Acquiring proficiency in time series forecasting is critical due to the characteristics of sequential data and significance in several fields, including finance, environmental research. The environment completed in ADT 5560 is to comprehend, construct, and enhance RNN models for the purpose of forecasting future data points and to comprehend the patterns and summarize in this report. First, let us go with part one, which is a time series dataset. So I have taken a dataset which is air quality dataset report, and the data type is time series data, and the source which I have taken this is UCM machine learning repository, which is a popular one. Here is the official website and download link where you can download the dataset. The dataset comprises a time span from March 2004 to April 2005. Coming to the data description, the dataset comprises 9357 occurrences of hourly average answers obtained from air quality chemical multi-sensor device integrated array of 5 metal oxide chemical sensors. The gadget was situated in the field in the road level region of an Italian city that was considerably polluted. Concentrations of CO, non-metallic hydrocarbons, benzene, total nitrogen oxides, and nitrogen dioxide were averaged hourly in ground truth by using the data from a certified analyzer that was co-located with the source. The data points. They are 9471 data points and 14 columns after cleaning up and pre-processing data. In the data structure, we have like several columns, each representing with different substances and conditions. Uh, Let me list out everything. They are date and time of the recording, CO concentration, tin oxide, non-methylene carbohydrates concentration, benzene, titanium, nitrogen oxides, tungsten dioxide, temperature, relative humidity, absolute humidity. Next, the data structure. The data columns include data timing of recording, concentration of CO, NMHC, benzene, NOx, NO2, sensor response from various gases, temperature, relative humidity, and absolute humidity. The sensors were calibrated before the data collection began, ensuring the reliability of the measurements. Coming to the results. The post-cleaning of CO concentration plot has a distinct seasonal pattern, perhaps indicating the occurrence of peaks that coincide with certain events of periods of the year. The time series outcome illustrates the fluctuating and dynamic characteristics of air quality, hence emphasizing the criticality of ongoing surveillance in the interest of environmental health. The identified pattern indicates that the dataset is very suitable for neural networks modeling since it has both the periodicity and the outliers required to test and run advanced forecasting models such as LSTMs and RNS with early observations spanning over an year. The data's high granularity offers a good basis of development time series forecasting models capable of reasoning accurate predictions of future data changes. Here comes the conclusion of part one. The examination of a data set reveals the complex and variable characteristics of data contaminants in the environment. The visualization and the data structures applied provide a complete perspective that not only facilitates the compensation of historic circumstances but also plays a vital role in the construction of prediction models that may be useful for generating timely alerts and guiding policy making. By using sophisticated neural network models to analyze the data, we may progress towards more proactive stance in the management of air quality and the reduction of its advanced effects of environment and human health. That's the end of part one. Let's move to part two. Part two is basically simple RNN with sine wave data. Here comes the design for the neural network, which is asked in the question. We can see the waves pattern starting from zero, going up to one, and then coming down to -1. This is based on complete input values which are given, and in the x-axis we can see the input values, and on the y-axis we can see the sign values. The architect overview. The neural network designed for this task is simply RNN comprising two layers. An input simple RNN layer followed by fully connected dense output layer. Here we can see two things and the output and the param. So in the from the below table we can see that the total params are 2651, trainable params are 2651, not trainable are 0. The input layer is designed to accept a single feature at each timestamp, which is design choice and aligned with the univariate nature of sine wave data. The buried layer consists of 50 simple RNN nanos. The function of this layer is to capture the temporal dependencies of sine wave data. The hyperlodic tangent deviation function is used for simple RNN layer. This function is often utilized with RNN because of its capacity to approximate non-linearities and mitigate the vanishing gradient issue to a certain degree. The output layer. The output layer is fully connected dense layer with a single neuron. It outputs the predicted value of sine wave at the next timestamp. Here comes the network data. Here we can see three things. One is input layer, simple RNN, output layer. On the left hand side, we can see input 1, input 2, input 3, going with the simple RNN layer, and here comes the output. Results of training and evaluating the model. First comes the training process. The model was trained using the generated wave sign data of 100 epochs with a batch size of 32. The kernel framework was used to facilitate the model construction, compilation, and training. The mean squared error was selected at a loss function, and the Adam optimizer was used to minimize. Evaluation metrics. The model was evaluated on a test set, which is about 20% of the entire data, which was a portion of sine wave data, was not seen by the model during training. The loss of this test set was recorded to access the model's performance. Training and validation loss. The training process resulted in a final training loss of and the validation loss. These very low loss values indicate the model was able to learn the sine wave pattern effectively and generalize well to unseen data. Lost plot. The plot of the training and the validation loss over the epochs were generated. It shows a random increase in loss, indicating quick governance of the model of high performance stage. Conclusion. Simple RNN designed for this project has proven to be effective in predicting the values of sine wave time series. The architect and parameters chosen for this neural network provides good results as evidenced by the low training and validation loss. That's the end of part 2. Here comes the part 3, which is LSTM neural networks. The vanishing gradient problem occurs during the data of deep networks, where gradients are passed back through the network for weight updates. If the gradient is very small, it gets very smaller and it is propagated backwards through the layers. As a result, initial layers may receive such tiny updates that are hardly alive. Imagine trying to listen a whisper in a storm that can be trying to catch the vanishing gradients. But they are so faint that they cannot cause much. Here we have like two diagrams, which is on the left hand side, on the right hand side. The left hand side is the vanishing gradient, and on the right hand side we have the explodent gradient. In both the graphs, we have layer on one of the axis and gradient on the other axis. In the vanishing gradient, we can see the gradient dropping off right from the output to input, and in between we have layer 1 and layer 2 and layer 3. And in the exploding gradient, it's completely the opposite. The wave completely goes up with the input uh, from the output, and we have like layer 1, layer 2, layer 3 in between them. Here you have a closer look on the figure. Comes the next question. Simple RNAs are a bit like short-term memory camps. They are great at remembering what happened a few moments ago, but ask them all to recall something from way back. They are stuck. This limitation is due to inability to maintain a longer constant, which is crucial with the input sequences have long-term dependencies, or when you need to remember information over longer sequences. They are also prone to vanishing and exploiting gradient problems I just described, which makes them very less likely to remember over longer periods. Here we have one of the figure. Now, the LSTM neural networks are like having a notepad to jot down all the important bits. They can decide what to remember and what to forget thanks to their internal mechanisms, aptly named gates. These gates control the flow of information, allowing LSTMs to maintain a longer memory and to be more robust when it comes to learning from longer sequences. Here is a figure for that. This means they provide powerful solutions to both vanishing and exploiting gradients by maintaining a more constant error using these kits. They can effectively skip over irrelevant parts of a sequence while selectively passing through the useful information, which makes them quite adept at addressing the limitation of simple RRS. Here comes part 4, design of the neural network. During deep network training, when gradients are transmitted back through the network for weight updates, the vanishing gradient issue arises. When a gradient is very modest, its magnitude decreases more when it is reverse propagated to the layers. Each layer may thus get updates for such negligible magnitude that they hardly learn. Attempting to discern a whisper among a storm is comparable to attempting to see disappearance of gradients. They are there, but their intensity is low that they are unable to affect a significant transformation. Here we have a figure for that. On the complete left, we have the input layer, and on the complete right, we have the output layer. And in between the input layer and the output layer, we have LSTM layer 1, dropout layer 1, LSTM layer 2, and dropout layer 2. From the input layer, we will be getting the output layer. The diagram illustrates the neural network architecture with all the layers explicitly marked. This includes input, LSTM, dropout, and dropout layers, showcasing the flow of data through the network and interconnection between different layers. Here comes a summary of core parameters. The LSTM network design is anchored by the following two parameters, which is the number of LSTMs is 2, neurons per LSTM layer is 50 in each layer, the number of dropout layers 2, dropout rate 20%, length of input sequence 10, batch size for training 32, batch size for testing and forecasting 1, and number of epochs for training 100. These parameters were chosen to balance the model's complexity with its ability to learn from the time series data without overlifting, ensuring a model that interacts well to unseen data. The results. The LSTM model underwent a rigorous training and testing process using a time series dataset. Build and train. Initializing a sequential model and including two LSTM layers interleaved with two dropout layers comprised the model construction procedure. Training was conducted in batches of 32 throughout 100 epochs. A reduction in loss at the conclusion of the training period indicated that the model had learned and adapted. Test. Testing the model on a separate set of data resulted in test loss of 0.003873, demonstrating the model's effective learning and predictive abilities. Retrain and forecast. Post-testing, the model was retrained on the entire dataset to fine-tune its weights for overcasting purposes. The retrained model was then used to forecast the next data point in the sequence, yielding a forecast value of 370.89895 ppm for atmospheric CO2 concentration. Evaluation. The valuation and the training and validation loss graph exhibits a downward trend, indicating a model cover. The occasional spikes in validation loss suggest instances where the model encountered previously unseen patterns, a natural occurrence in time series time series prediction task. The forecasted value aligns with the unexpected seasonal patterns observed in the dataset, indicating the model's potential utility in practical forecasting of appliances. Here comes part 5. Redesign the neural network. So here we have like 8 things which we are considering for the redesign of neural networks. The first one is percentage of data for testing. So we have to maintain a 20% testing spread to ensure enough data is available to validate the model's performance while maximizing the training data. Number of LSTM layers. Introduce additional LSTM layer to capture more complex pattern and long-term dependencies in time series data. Number of neurons per LSTM layer. Increase the number of neurons in each layer to allow the network to learn more complex representations. Dropout layer. Include dropout layers to prevent overfitting, especially since we are increasing model complexity. Percentage to drop. Adjust the dropout rate to a slightly higher value to compensate for the increased number of neurons. Length of input sequence. Increase the length of the input sequence to provide more context to the network for each prediction. Batch size for training. Reduce the batch size to allow the model to update weights more frequently. Number of epochs running. Increase the number of epochs to give more complex models sufficient time to learn. Next, redesign the neural network. The design of LSTM neural network has revisited the enhanced and its performance of the time series forecasting task. Drawing from the experiences gained in various parts of the project, critical changes were implemented. They aim to refine the model's ability to capture underlying patterns within the data. Here we have the diagram with the input layer on the left and the output layer on the right. In between, we have the layer 1, layer 2, layer 3 with LSTM and dropout. Summary of updated core parameters. The following parameters were adjusted in the redesign of LSTM network to potentially improve its performance. Number of LSTM layers increased to 3 layers to allow the model to capture more complex features and temporal dependencies in the data. Neurons per LSTM layer configured to 64, 64, and 32 respectively to enhance the model capacity for learning. Dropout layers included after each LSTM layer to prevent overfitting with the number of dropout layers being 2. Dropout rate set to 25% to mitigate the risk of overfitting due to the increased model complexity. Length of input sequence extended to 20 to provide the model with more contextual information for predictions. Batch size. Batch size for training reduced to 16 for more frequent updates of the model weights. Next, number of epochs for training increased to 150 to ensure the model has ample opportunity to learn from the data. Report on the results. Model training and validation. The revised model underwent training for a total of 150 epochs, during which the training loss decreased gradually. This explained the model's ability to acquire knowledge effectively from the training data. Nevertheless, the validation loss exhibited a degree of instability punctuated by intermediate spikes that may indicate overfitting or the existence of complex pattern in the validation dataset that proved very difficult for the model to identify. Testing a redesigned model. Upon testing, the redesigned model achieved a test loss of 0.0018107, signifying a robust generalization to unseen data. This test loss is an indicator of model's accuracy in predicting the time series. Retraining and forecasting. Retraining the model on the whole dataset was later conducted to refine the prediction capabilities. Despite a minor increase, the loss recorded during this period remained within unacceptable range. The result of using untrained model to make predictions was 372.475 ppm, although this value cannot be verified in the presence of clear future data. Training and validation loss plot. Here on the x-axis we have the epochs, and on one side, on the other hand, we have the losses. So the blue indication is the train loss, whereas the orange is the test loss. The model learning process is confirmed by the overall decreasing trend in training loss as seen in the plot of training and validation loss. Spikes in the validation loss indicate instances in which the model's predictions exhibited a significant deviation from the truth values, hence indicating potential domains for enhancing the model's reliances. Critical analysis and conclusion. The LSTM network redesign experiment was predicted on the application of acquired knowledge and critical analysis to suggest rational modifications with the objective of improving the performance of the model. Although the adjustments made did not result in a constant increase in the validation loss, they did provide a minimal test loss, which is an encouraging development. The experiment, the experiment serves as a tangible illustration of iterative process. It is encouraging development, and the experiment serves as a tangible illustration of the iterative process involved in the development, emphasizing the criticality of ongoing thing. The experiment methodology and the results underscore the significance of not just implementing machine learning method but also subjecting them to rigorous evaluation and trading information to attain optimal information. The combination of iterative methodology and the readiness to engage in experimental is critical for progress in the domains of machine learning and data science. Here comes part 6, compare network performance. We have built, trained, and evaluated two distinct LSTM neural network topologies with great attention in detail in prior phases of history. Performance compared. The first LSTM network, categorized by its two-layered architect and 20 neurons per layer, yielded price-worthy outcomes. The test loss of 0.0038073 was attained, indicating a satisfactory level of fit to the test data. Network demonstrated proficiency is discerning the seasonal patterns and trends inherited in the time series data as seen by the predicted CO2 concentration of 307.897 parts per million. In contrast, to increase the learning capacity of the model, the revised network included an additional STM layer and a variety of neural configurations, 64, 64, and 32 neurons respectively, in order to provide the network with more contextual information. For each prediction, the input sequence was lengthened and the dropout rate was marginally raised. Notwithstanding these refinements and the test loss of, of the new model barely improved to 0.0018107, and marginally enhancement in test loss suggests that the model has but not significantly improved its forecast. Analysis of the results. After refining the total model using a whole dataset, a predicted value of 372.475 parts per million was acquired. Although empirical verification of this predicting value is not unattainable in the presence of real future data, it aligns with the predictions of the patterns in prior data. It is worth mentioning that the validation loss of the modified model displayed highlighted inequality characterized by unnoticeable spikes through the training epochs. This observation may indicate an overfitting, heightened sensitivity, and patterns generated by the modifications. This is shown by the training and validation loss plots generated and modified model. Although training loss exhibited a constant decline, suggesting a robust learning trajectory that spikes in validation loss suggestion possibility overfitting of the model. Conclusion. The model redesign iteration was guided by insights gained from the first training phase and throughout assessment of the network architecture. The modifications included in the modified model resulted in somewhat enhanced test loss, however, not a comparison performance improvement. This result is relatively uncommon in machine learning projects, whereas gradual inputs are often seen and not in a significant breakthrough. In order to build the LSTM network serves as evidence of the proprietary nature inherited in the field of machine learning. It asserts the development in the content to the application acquired information in critical learning. Even in cases when the measures used to fail provide significant influence, the process of redesigning underscores the significance of explaining data. Here comes part 7 to the project report. Part, part 2 included the development of simple RNN to a process of sine wave dataset. The experiment provided a fundamental opportunity to get insight into fundamentals of RNNs and their capacity to represent sequences. The periodic and continuous nature of the sine wave provided the RNN with distinct pattern to learn and predict. Part 3. Understanding RNS limitations. The theoretical limitations of RNS, including the vanishing and exploiting gradient concerns, were examined in Part 3. This investigation revealed the reasons of why RNSs could have difficulties when confronted with lengthy sequences. The knowledge acquired established the foundation for the implementation of more advanced models such as LSTMs. Part 4. LSTM with time series data. Subsequently, in Part 4, a LSTM neural network was implemented to process a real-time time series dataset included atmospheric CO2 concentration predictions. The design of LSTM, which had memory cells and gates, was a substantial advancement over the simple RNA, enabling it to capture long-term relations within the data and more fluency. Part 4. Part 5. Redesigning the neural network. And kept with the insights and expertise gained in preceding station, the LSTM network underwent a redesign in Part 5 with the intention of future optimizing its performance. So fine-tuning parameters and layer count, neuron count, and epoch duration. The network's capacity to acquire knowledge from the dataset was refined, leading to development of the more precise forecasting model. Learning and experiences from the model. The disparity between simple RNS and LSTM became conceptually evident throughout the course of the study. In contrast, the shortcomings of simple RNSs were compared to the reliance shown by LSTMs, particularly when confronted with diminishing gradients and while learning from longer sequences. The particular implementation of constructing, training, and evaluating these models serve to clarify the of neural networks and emphasize the criticality of inference and exploration in the field of machine learning. Here comes the conclusion. Summary of this project report serves as evidence of the scholarly expansion of the domains of LSTMs and RNSs. Particularly for time series forecasting, it offered vital insights to the particular elements of neural network architecture and optimizing. By construction testing and improving the models alternately, not only was more profile comprehension, but the mechanics of RNS illustrated, but also the critical thinking necessary to adapt agents and machine learning models were also ongoing development of the artificial intelligence and experiences detailed in the publication will provide a strong basis of the addressing increases complex challenges and making contributions in the forefront of technology. And before concluding the final project report, I would like to thank uh, Dr. Professor Dr. Newell for giving me this opportunity and exhibiting myself, and both of our TS, Dinesh and Nirupama, for guiding us in everything in this coursework. Thank you, guys.